me recording? Okay, small victories. All right, we are going to be looking at the pH and the pOH scales, okay? Because there is also something called pOH. Now, as hydrogen gets higher, pretend that doesn't work. There we go. As hydrogen increases, pH does what? Decreases. So a low pH is acidic. And a high pH is basic. By the way, let's remind ourselves of some properties of acids and bases. If something is acidic, what will some of its properties be? Sour. Oh, it turns litmus. What color do acids turn litmus? Red. It's sour. It turns litmus red. What? It's sticky? Reacts with some metals. Instead of corrosive, we're going to say it reacts with some metals. If you've forgotten, that little C with a dash is with. Okay, react with some metals to produce H2 gas. Acids are sour. Soluble in water. Oh no. I know, senior moment. I'm not quite senior yet, but we're trying. Let's see what it has to say. Acids. I should just know this. It's like the easiest thing in the world. Okay, sour. Oh, they react with bases, of course. I know that seems silly, but they react with bases. No wonder I forgot, because it seems so blinking obvious. So that's 1, 2, 3, 4, and the fifth one is that they are something that starts with an E, electrolytes. Now, if you're wondering where I found this, this is Hebden, page 111. Okay, so if you now, I'm sorry, I'm gonna go off the page. If acids are sour, what are bases? Bases are bitter. They turn litmus blue. Now, they don't have an equivalent one for react with some metals to produce hydrogen gas, but instead, they feel slippery. And what else do they do? They react with acids. And finally, They are electrolytes. Does everyone remember what an electrolyte is? An electrolyte has ions in solution. And therefore you have mobile charges. And therefore the solution will conduct electricity. Electricity. So sour, bitter. Litmus red, litmus blue. React with some metals to produce H2. Feels slippery. Those ones don't match up, right? React with acids, react with bases. And then we have, oh, look at all the different colors I have here. But I want something, oh, the one I had at home had this lovely like light purple color, but I don't see it here. So it's gonna be too hard to find, so I'm gonna use light blue. They are both electrolytes. So it's like different, 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 the same. Is good? Okay. So high pH is acidic, low pH is basic. What? Did I say that wrong? I said that totally wrong. High pH is basic, low pH is acidic. Okay. Each number on the pH scale represents a 10 times change. What kind of a scale is that if every time you move up, you're changing by a power of 10? That is a logarithmic scale. Okay, so if you are at pH 7 and the solution changes to pH 6, you have 10 times the hydrogen ion concentration. So if you start at 7, pH 7, you move to 6, the hydrogen ion concentration has gotten 10 times higher. If you start at 5 and move to 3, this is 2 pH units. And so it changes by 10 to the power of 2. So if you move 2 pH units, it changes by 10 to the power of 2. If you move 1 pH unit, it changes by 10 to the power of 1. Because 10 to the 1 is 10, and 10 to the 2 is 100, yes. Yeah, we'll get to that. Don't worry, we'll figure out how to do all the calculations. Okay. Now let's look at this one here. We're going from 8 to 11. Are we becoming more acidic or less acidic? We're becoming less acidic. And how many pH units have we moved over? 1, 2, 3. Okay, so we have moved 3 pH units. And so the concentration of hydrogen has changed by 10 to the 3. I guess I should put concentration of hydrogen here. That would make it more obvious what I'm talking about. And then you just look at which direction you're moving. If you are becoming lower, hydrogen is increasing by a power of 10 to the whatever. If you're getting a higher number, it is the hydrogen ion concentration is decreasing by a power of 10 to the whatever. To have a very low pH, you either have to have a strong acid, because a strong acid will produce a high concentration of H+. At most concentrations. Are we talking about chemistry or are we just talking? Okay. A strong acid will produce a high concentration of H+ at most concentrations. Why is that? Because it completely dissociates. Now you can get a low pH by having a weak acid, but it has to be really, really concentrated, because if it's not really, really concentrated, like very little, like 1/1000th of it maybe, or 1/10,000th, or 1/10 or 100,000th is how much actually splits apart. Yes? You can see how it's really hard to get a high concentration if a very small amount is actually splitting apart. So you would have to have a fairly strong-ish weak acid. There are stronger weak acids and weaker weak acids. You would need to have a fairly strong weak acid at a fairly high concentration to get anywhere resembling the low pH you would get with a strong acid. Okay. All right. So here's our strong acid. At most concentrations, you end up with a really, really low pH. Here's carbonic acid. It's a weak acid. How many hydrogens does it give off? Not very many. How many does HCl give off? Lots. Okay, so any concentration basically, unless it's like, 0.000004 or whatever, there's a lot of zeros, almost any concentration, well, I guess at any given good concentration, a strong acid will have a lower pH than a weak acid, but all right, let's fill this in. As pH increases, what happens to hydrogen ion? Decreases. As pH decreases, hydrogen ion increases. Now here's a tricky one. As hydrogen ion concentration increases, what happens to concentration of OH minus? I'm going to show you a little thing about water. Water actually does the following. Water can actually react with water, and it can act as a Bronsted-Lowry acid, and the other one can act as a Bronsted-Lowry base. Now, let's remind ourselves, tell your partner, what is a Bronsted-Lowry acid? What is a Bronsted-Lowry base? is a Bronsted-Lowry acid? Yes. Yes, it is a species that can donate a proton to another species. Can I just call it a proton donor? Okay, it is a proton donor. What do we mean by proton? H plus, because remember, if you have a hydrogen atom, you have one proton in the nucleus and you have one electron. Yes? When it becomes the H plus ion, what were we left with? Just a proton. Okay, and that's why we call H plus ion a proton. What is a Bronsted-Lowry base? It's a proton acceptor. So let's go back here and look at, where did it go? We were on 4.1 what? 4.2a, 4.2a. Okay, good. So if this water is a Bronsted-Lowry acid, what's it going to do with its hydrogen? It's going to give a hydrogen to the other water. So far, so good? So the one that has given away its H plus, what is left at the end? If H2O gives away a hydrogen, don't write this part down, we have only how many hydrogens left? One hydrogen. Are we going to write it as HO? No, we're going to write it as OH. And we lost not just an H, but an H plus. If we lose an H plus, it's going to be OH minus. And now we have our other water. It's H2O. And it accepts a proton. What is it going to become? Yeah, we now have 3 H's, an O, and we gained an H plus, so it will be positive. Do you remember the name of the H3O plus ion? That is the hydronium ion. Now, so we've reviewed a little bit of terminology: Bronsted-Lowry acid, proton donor; Bronsted-Lowry base, proton acceptor. A proton is a hydrogen ion, and a hydronium ion is an extra H plus stuck onto water, H3O plus. So we now have those vocab words. There's another vocabulary word that we could associate with water here. I would like you to chat with your neighbor and see if you can think of what it is. How is water behaving here? There's a special word for it. Water is what? What's that word? Wet. It is wet, which might make you think of something that lives in a wet environment, like a amphibian, like a frog, or any kind of amphibian. And what does amphibian, why is it called an amphibian? Why the amphi? They can live both on land and in the water. They can get their oxygen both from the air and from dissolved oxygen in the water. So if water is wet, water is amphiprotic. That's not why it's amphiprotic, but that's okay. It is amphiprotic because it can act both as a proton donor and as a proton acceptor. Okay? So amphi means both. I tried to make a small b and it became a big B. I don't know what I'm doing there, but that's okay. Water is amphiprotic. It's both a proton donor and a proton acceptor. So in other words, it is both a Bronsted-Lowry what? Acid, and a Bronsted-Lowry base. Look at us reviewing terms left, right, and center. Isn't that awesome? Okay. This process that we've written up at the top of the page, this water plus water, gives hydronium and hydroxide. This process is known as the autoionization. Do you guys know what auto comes from? Self. Well, yeah, because if the plane is on autopilot, who's driving the plane? The plane is driving itself. So auto means self. Yes? The automobile, who is driving the automobile? Who is making the go forward? The automobile is making the automobile go forward. Okay? So auto means self. So water is reacting with itself to become ions. Water is acting with itself to become ions. So this is the autoionization of water. What do we have here? We have an equilibrium. What's going to happen if I add some acid to that equilibrium and the hydronium ion concentration increases? Because if I add acid, I get hydronium. It will shift to the left. Now I would like you to figure out what happens to the hydrogen ion concentration or hydronium ion concentration and the hydroxide ion concentration when it shifts to the left. I'm actually going to pull up some paper again for that. Here we go. So if you add an acid, it increases the concentration of hydronium because hydrogen doesn't actually float around in water, right? There's no actual like H plus floating around. H plus always gets together with water and produces H3O plus. So if I've got HCl, the HCl will dissolve in the water, okay? And in fact, I can even do it like this, yeah? And I can say HCl is the Bronsted-Lowry acid, and if water is reacting with an acid, it is going to act as a base. Bronsted-Lowry base. So here comes our hydrogen ion. Hydrogen, HCl is giving it off, it's giving it to water. And we're left with Cl minus, which is going to be a spectator ion. It's just going to hang around and do nothing. And what's our other ion that we have? H3O plus. And this is a one-way arrow. So this is what is really happening. This is reality. Okay. What we will often write is the shorthand. You guys don't know what shorthand is anymore, do you? Do you know the expression shorthand? Shorthand is a faster way of writing. There used to be an actual way of writing that was called shorthand, and it was made of little squiggles and whatsy-doies. So because you didn't used to be able to dictate into a thing or whatever, and so the secretary would sit there and take down shorthand notes and then would transcribe it and type it all up for you on a typewriter. Okay, the shorthand method, we're just going to write it a little bit shorter, is to write HCl goes to H plus plus Cl minus. So that's what we've been writing up till now, yes, when we've been writing a dissociation. And I know the H and the Cl are in a different order. Does that matter? Does it matter that I wrote the H3O plus second and the H plus first? Nope. Okay, because these guys are the same, essentially. If we say hydronium, if we say hydrogen, we really mean hydronium, okay? Hydrogen is just the shorthand for hydronium, which is what we have in reality. Yes? Honestly, if it doesn't ask you, I would do the second one because it's faster, but you should really be aware that the first one is what is actually happening, okay? So, here we have our autoionization of water. When we add acid, here we've added our acid. And when we add acid, what do we get? We get hydronium, yes? So when we add acid, what do we get? Hydronium. We add acid, what do we get? Hydronium. We add acid, what do we get? Hydronium. I mean, you could say hydrogen, but we're going to say hydronium. So what does that do to our autoionization of water? It's going to shift it to the left. So the hydronium ion concentration increases. That's going to shift it to the left. So number one, concentration of H3O plus. Whoa, that's a bad bracket. In fact, I'm going to say number one, we add an acid. Add acid. 2, concentration of H3O plus does what? Increases. 3, the equilibrium, this one, shifts left. I would like you to predict how the final concentration of hydronium and the final concentration of hydroxide compare to the original hydronium and hydroxide concentrations in pure water. Are we predicting or are we just chatting? You already predicted. What did you predict? H3O plus is going to increase, and OH minus is going to decrease. Could we draw a concentration diagram for that? Yes, we could. So initially, we have pure water. We have the hydronium ion concentration. And we have the hydroxide ion concentration. And pure weight. Okay, I'll put a R in there. Pure water, they are the same, yes? They're the same, yes? Is that true? Yes. Because when it dissociates, when the water dissociates or when it autoionizes in a 1-2-1 fashion. Yes? We have a, where did it go? Autoionization, we have a 1-to-1 relationship. When it dissociates, they're equal. All right, now we add some acid. What happens? Hydronium goes up. What happens to hydroxide in that instant? Nothing. And then what happens as time goes on? Both concentrations are going to go down. Hydrogen will go down. How far will it get? Above the original. So hydrogen goes lower, but it's above the original. What happens to hydroxide? It goes down by how much? Same amount because they react in a 1-to-1 fashion. So the final concentration of H3O plus is higher than initially, which you predicted. And the concentration of OH minus is lower than initially, which you also predicted. Yay! Okay? So anytime you increase hydronium, the hydroxide goes down. Anytime you increase hydroxide, what happens? The hydronium goes, ooh, you want to try that one? Pure water. We are now going to add a base. We're going to add some NaOH. What happens? Yes, sorry. At the beginning? In pure water? Yeah. Okay, so in pure water, what you have is you have water reacting with water. And every time you make one hydronium, you make one hydroxide. Equal. That's it. Okay? So that's what we have when we have pure water. 1-to-1. So H3O plus is equal to OH minus. But now what we're going to do is we are going to add some sodium hydroxide. What happens to this equilibrium when we add sodium hydroxide? First of all, what does NaOH do in water? Let's say it starts as a solid. What does it do? It dissociates. Because remember, big B are your strong bases, and all alkali compounds are soluble. So we've added NaOH. What have we changed that relates to the equilibrium? Yes. But before you go, what have we changed that relates to the equilibrium? Yes, you may go. Okay, so concentration of hydroxide has gone up. Therefore, which way will this shift? It'll shift to the left. So concentration of hydroxide goes up, and then hydroxide will come down, but it will be still higher than its original level. I don't know, this time I didn't make it go down as far. It really doesn't matter. Okay, X, it goes down by X, yes. Okay, and then hydrogen, or in other words, hydronium, H3O plus. You'll notice that I use hydronium and hydrogen interchangeably, and sometimes I'll be in the middle of using one and I'll switch to the other just because my brain really doesn't distinguish between them very well. So if you ever get confused about what I'm doing, let me know and I can clarify, okay? So this is H plus, H3O plus, and this is OH minus. So if we add a base, the hydroxide ion concentration has gone up and the hydrogen ion concentration has gone down. Is good? Excellent. Does anyone feel like they'll want me to print these notes off for tomorrow? Yes? Okay, I will do so. Oh, hang on, 4.28, there we go. If you add water, you just still have water, right? Because does water have a concentration? No, okay? So now we can go back here and say what happens as hydrogen increases, what happens to hydroxide? As hydrogen increases, hydroxide decreases. As hydrogen decreases, hydroxide increases. And remember, pH scale is a logarithmic scale. That means each pH unit is 10 times, either more or less, depending on whether it gets bigger or smaller. each pH unit is 10 times more or less than its neighbor. I mean, like if you're pH 6 and you go to pH 7, or if you're 7 and you go to 8, or 8 and you go to 7, or whatever. If pH doubles, does hydrogen ion concentration double? No. For every change in a unit of pH, H plus changes by a factor of 10. Now, here's some fun. This is how it works. pH, P, power of H, the hydrogen ion. P, power of the hydrogen ion, pH. So if the pH is 2, what is the power of 10 for the hydrogen ion? Actually, I should say power of 10 of the hydrogen ion. So if the pH is 2, the power of 10 for the hydrogen ion is 2. Okay, not rocket science, not looking for a complicated answer here. Okay, if pH is 2, that means the concentration of hydrogen is 10 to the 2 molar. How much molar is that? Oh, sorry, I'm wrong. It's 10 to the negative 2. Ten to the negative 2. So what is that? What is that in decimal version? 0.0 0.02? No. Remember, 10 to the negative 2 is the same as 1 over 10 to the 2, which is the same as 1 over 10 times 10, which is equal to 1 over 100, which is equal to 0.01. So if you have a pH of 2, hydrogen ion concentration is 10 to the negative 2, all right? And so that means we have a 0.01 molar concentration of hydrogen. If pH is 4, what is the concentration of the hydrogen ion? 10 to the negative 4 molar. And what is 10 to the negative 4 in decimal format? 0.0001 molar. So pH changed by 2 units pH has the pH, so the pH has, no, hydrogen ion, this should say hydrogen ion, not pH. Hydrogen ion has increased or decreased? Decreased. Remember, if the pH gets bigger, the hydrogen ion gets. If pH gets bigger, hydrogen ion gets smaller. Why are we doing this? Oh, I see. So pH is decreased by a factor of how much? 10 to the 2. So all you have to do to figure out how much hydrogen is changing, like let's say we changed from, oh yeah, here we go, pH decreased from 7 to 4. What has happened to the hydrogen ion concentration? First of all, you can say pH got lower, therefore concentration of H plus, did it increase or decrease? Increased. And by how much did it increase? Well, 7 minus 4 is 3 units, so the pH changed by 3 units. And if it changed by 3 units, that means that the concentration of hydrogen ion changed by a factor of 10 to the 3, right? So if pH changes by 3 units, hydrogen ion is going to change by a factor of 10 to the 3. And so we know hydrogen ion increased by a factor of 10 to the 3. So in essence, it's gone up by 1,000 times. Yes? Okay. Is good? Okay. Another related scale is the POH scale, which is essentially the opposite of the pH scale. Let's take a look at our pH scale. We haven't really talked about it in depth just yet, but it goes essentially usually from 0 up to 14. You can actually get negative values, yes, of course. You can actually go above 14, okay? So this can get lower. It can go, G. It can go negative. And the pH can get higher. What's wrong with me? Why can't I write? It can go greater than 14. Okay, so it can become less than 0 or greater than 14, but we are used to having a pH scale that goes from 0 to 14. That's sort of the normal range of pHs. If you have concentrated hydrochloric acid, which means it's as concentrated as you can get, and you can't go any, it can't get any more concentrated than that, that's going to be a pH of probably about -1. Okay? So it's hard to get below that, right? And it's also hard to get above 14. If you have sodium hydroxide at a concentration of 10 molar, you can get above 14. But it's hard, because at some point it just stops dissolving in water. You have a question? Why is 7 neutral? Oh, this is beautiful. Shall we go back to our autoionization of water? H2O, H2O. What are our products of the autoionization of water? Hydroxide and hydronium. Okay, and we agreed that happens in a 1-to-1 fashion, yes? And this is an equilibrium. What do all equilibria have? They all have a K value, okay? And the K for the autoionization of water is called KW, okay? Oh, I shouldn't have written that so far. Here, I'm going to make this a little smaller. Okay. Water's a liquid, hydronium is aqueous, hydroxide is aqueous. What's the Kw expression? Concentration of? I'm going to write H3O plus just because it's like, we always write H plus first or H3O plus first. But there's no good reason. You could write hydroxide first. No good reason why you couldn't switch those. Because 2 times 3 is the same as 3 times 2. Now, the value of Kw at 25 degrees Celsius, Kw is equal to 1.0 times 10 to the negative 14. So we have water and we have water. Shall we do a rice table? R-I-C-E. Initially, let's just assume we created water out of nothing. Okay, we create some water. So initially, what are the original concentrations of hydronium and hydroxide? If we just created water, they're 0. Oh, look at that. Now, water is going to react with itself. So what's the change going to be? X. Yes? And at equilibrium, X. So we now have Kw is equal to H3O plus times OH minus. We can substitute in all our things. What's Kw? 1.0 times 10 to the negative 14. And then H3O plus is X and OH minus is X. So we have X squared is equal to 1.0 times 10 to the negative 14. And therefore X is equal to 1.0 times 10 to the negative 7. Yes. And remember, if you have a pH of 7, then the hydrogen ion concentration is, or hydronium ion concentration is 10 to the negative 7. Yes? Yeah. So that's when they're equal. That's only at 25 degrees Celsius, because what does changing temperature do to a K value? It changes it. Yep. So for example, I'm going to just go and quickly look up the K value for water at, shall we say, 75 degrees? Yes. Yeah, for sure. Let's see what we got. Kw of water. Oh, my phone is starting. Here, let's see if we can do it here. It updated this morning. This might be faster. Kw at 75 degrees Celsius. 1.995 times 10 to the negative 13. Okay. So for example, 75 degrees Celsius, Kw is equal to 1.995 times 10 to the negative 13. Whoa. So what is the concentration of hydrogen and the concentration of hydroxide at 75 degrees Celsius in your water? Do you guys think you could solve that? What? 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 Oh, I texted my husband last night because he wasn't, no, on Monday night, and I said, are you out tonight? Because he was out at around 5:30, and I'm like, am I having dinner by myself? Like, I just don't know. And he replied, sometime between when I updated my phone and now, today, Wednesday, no. And I'm like, okay. I'm like, no, because I just got a notification on my watch, and it says Phil Northcott, no. And I'm like, no what? No what? No? Anyway, we're not the best communicators over like texting. Neither of us are really good about getting back to each other, so it's okay, we understand each other. If I don't get back to him, if he doesn't get back to me, it's all good, right? Because neither of us are good at it. There's no imbalance in that relationship. Much like hydrogen and hydroxide. Yes, exactly. There's not very much of either of them, but they're in perfect balance. Yes. All right, so what would we do to get the concentration of hydrogen and hydroxide? And you know what I'm going to do, actually? I'm going to write the autoionization of water in shorthand for the autoionization of water, because I'm lazy. H plus and OH minus. Is that good? So you can either write it with the two waters. Are we on our phones or oh no, we're on our calculators? That's okay. I'm all right with that. So we have the H plus, we have the OH minus. Kw is equal to, what is it equal to? No, it's not yet, because you always need to write the expression first. Good habit, okay? I know you know to do that, but I'm reminding you once again. So we have 1.995 times 10 to the negative 13 is equal to x squared. Okay, 1.995 E13 negative root. So x is equal to 4.4665 times 10 to the negative 7. Now, here is the formula for calculating pH. We know that if we have 1 times 10 to the negative 7, if that is our hydrogen ion concentration, then the pH is equal to 7. Yes? We know that if we have a hydrogen ion concentration of 1 times 10 to the negative 3, then the pH is 3. Okay, those are easy. But we have a number that is not 1 times 10 to something. Yes? So in order to get this number, which is this number, yes, we need pH is equal to, how do we get from 10 to the 7 to 7? What function do we do? We do the log, yes? But if it's 10 to the, how do we get from 10 to the negative 7 We take the negative of the log. Yes, we take the log and then we make it negative. So pH is the negative of the log of the concentration of the hydrogen ion. You must know that formula. Okay? So could you find the pH? This is our hydrogen ion concentration. Could you find the pH of neutral water at 75 degrees Celsius? Look at that. What's the water like? The water is neutral. Is the pH 7? No. So neutral is only pH 7 when water is at 25 degrees Celsius. This is the pH of neutral water at 75 degrees Celsius. pH 7 is neutral only at 25 degrees Celsius. Elliot. Yeah, they feel relative to each other. So if you have a pH at 25 degrees Celsius, if you have a pH of 4, you'll have a pOH of 10. Yes, because they'll equal 14. Yeah. Your homework is to do that weak bases thing and then to go through any thermodynamic stuff if you have extra time. I will put that on Teams. Yes? As you heat water up, it does not get acidic because the OH also goes up. So it is still neutral. We'll add that on next day. Yes, Daniel? 60, it'll be somewhere in between 6.35 and 7. You would have to be given the KW value, right? I had to look up the KW at 75 degrees to do this. So you would have to be given the KW at whatever temperature. Happy. Thank you. And I do have a little collar on because the little tag is made of metal, and metals become anions. Right? That only came to me this year. 28 years, I'm still coming up with new things. Here's a different thing. Here's the thing. Okay.
봤는데 김우면이죠. 퀴즈 수업 써 있네.
얘 맛있나봐 맛있게.
your quizzes before I forget. Okay, so we have the atomic experiments, the enriched portion, and then we'll all get back the periodic. Actually, we'll do the periodic table quiz first, and then we'll do the other part. So when you hear your name, come on up and grab your quiz. Anne, Borna, Adri. Thank you, thank you. No, Sunny. No, you're not going to fail. You didn't fail. Jenny. Kayla. She did not fail. No. Ninji. Juan. Tanisha. Rihanna. Yes. Okay, thank you so much. Jonah has a track meet. Rachel. Aaron. Not here. Maya. Alexia. Not, oh, yes, you are here. You were just hiding behind Rachel. There you go. Kira. Luana. Oh, yeah. And I was like, oops. So, you know what? Why don't you just, when you have a chance, do the rest of it and hand it in? Yes? Okay, there we go. Michael. Jonas. Erica. Not here. Thank you. Leanne. Jasmine. Olivia. Jaden. Rehan. Sophia, I just finished giving back the quizzes, but yours is on my desk somewhere, and I don't know where, so I'll get it back to you tomorrow. Okay? Minji. Aaron. Sunny. Aaron. Oh, Aaron's not here. Why am I calling Aaron again? Joanne. Olivia. Kayla. Rachel. Riona. Jaden. Riona's not here. Jenny. Tanisha. Anne. Max.
Thank you.
You did it very punchy. Try one more time. Okay? Yeah. Adri. Sophia. And I have some older quizzes here. Okay, good stuff. So if you are unhappy with your quiz mark, of course, what can you do? You can re-quiz it. If there's time in class, that's great. If not, after school or during flex, both work for me. Anytime this week or next week would be good. Okay. Woo! Tripping over things. Okay, what do we, oh my gosh. Been recording all